Hey everyone, it's Bradley Bush with another algebra video. Today we're talking about systems of linear equations in three variables. Specifically, though, we're talking about the case where you have infinite solutions. So there are three different cases: no solution, infinite solution, and one solution for this type of a problem. And today we're talking about the infinite solutions case. So just to remind you, we have three variables. So we're in three-dimensional space. And the first thing we'll do is we'll have a quick overview of systems of linear equations. Then we'll do an example where you will see the infinite solutions case play out. So let's start with the overview. All right, so you're wondering, what is a system of linear equations in three variables? Because it sounds kind of complicated. Well, let's break it down because it really isn't that bad. So if you look at the three variable part of this definition, it just means we have equations in our system, and our equations have three variables. Usually they're x, y, and z, but they could be any three variables that we want. The next thing we should point out is that these are linear equations, which means the equations all fit the form ax plus by plus cz equals d, where a, b, c, and d are just constants, and x, y, and z are your variables. Something that's also important is that you won't ever have exponents that are 2, 4, 6, 3, 1/2. They all have an implied exponent of 1. You don't see it, but it's implied that it's there. So you'll never have anything crazy. You'll just see the x, y, and z variable, or whatever the variables you have. So because they're all linear, this means we have a plane, which is like an infinite sheet of paper in three-dimensional space. So think in your head, you're holding up a sheet of paper in your hand, and you're in a room, and that sheet of paper just extends in all directions. So not too bad, right? The last thing we should probably mention is that, what is a system? What does that word mean? Well, it just means you have more than one sheet of paper, more than one equation, or more than one plane in three space. So in our problems, we almost always have three equations. So those three equations make up what mathematically they call a system. So it sounded pretty horrible, but not today. It's not bad. Not bad at all, actually. Here is an example of a system. This system, specific system, has three equations. Equation 1, equation 2, equation 3. I label my equations with numbers and then circles around them, so you know. And this specific solution is -1, 2, and -2. So it's an x, y, z coordinate. So in other words, if you're wondering what a solution is to a system of three variables and three equations, it really is just any x, y, z coordinate, or any point in three space that lies on all three planes at the same time. So this point up here, -1, 2, and -2, is the point that happens to lie on all three of these equations or planes in three space at the same time. Not too terrible. Here's some graphics that really kind of help us understand quickly the different solution scenarios. So I said earlier that there are only three possible solution types. One is that you have one solution. So in other words, a single point is the only place that all three of these planes touch. So on the first graphic, you can see that there's only one point in all of the area where all three planes touch. Same thing for the second graphic. That yellow point is the only point where all three of these planes touch. You could have the no solutions option. You see in this first graphic that all of the planes, the three planes here, the purple, the red, and the green, they're all parallel. They never touch. There's no point that can be on all three of them at the same time. And the same with these last two pictures. You notice that here along this first yellow line, that's where the green and the red planes touch. Along the second yellow line, that's where the green and the blue planes touch, but the red and purple planes never touch. And the last graphic looks kind of like a capital A that's been rotated. So you can see here's a spot where the purple and the red planes touch. Here's a spot where the purple and the green planes touch. Here's a spot where the green and the red planes touch, but you never have a spot where all three of them touch simultaneously. So these would be the no solution category. And then finally, we have a category that you have infinite number of solutions to your system. So there are an infinite number of points that are on all three planes at the same time. And you can see that right here with this vertical yellow line. I've tried to draw a bunch of dots on here. I don't know if you can see them, but there are a bunch of points that would make up a line. And it's infinite. It goes all the way up and all the way down. So there are an infinite number of x, y, z coordinates that satisfy these three equations. How do you know which of the options you're in when you're given a system? It's a great question. It can be kind of confusing. So if you're solving a system and you get an answer, then you know that you're in option number 1, which is just one solution. Otherwise, as you're solving the system, at some point all the variables will drop out and you'll just be left with numbers. If those numbers and the equal sign make a true statement, meaning 0 equals 0 or 2 equals 2, then you're in the infinite solution category. So we should be watching for this specific scenario to play out in our example below. If you are going along, the variables drop out, and what's left is a false statement mathematically, like 0 equals 2, which is not true mathematically, then you know you're in the second option, option number 2, where you have no solution. So how do you solve these systems of linear equations in 3 variables? Well, they're a lot like systems of linear equations in 2 variables. You use the substitution and addition method, and then you just add one extra step. So what we do is we take 2 of the 3 original equations, and we use the substitution or addition method to eliminate one of the 3 variables that we have. Then we take that gives us another equation. We take that new equation that only has 2 variables, and we put it aside. Then we go back to our original 3 equations. We choose 2 different equations and eliminate the same variable that we eliminated the first time. Then that will give us another new equation. We take that and put it aside also. Now we have these 2 new equations that only have 2 variables. So then we can use the substitution and addition method to solve for those 2 variables. Once we have those 2 variables, we back substitute, meaning we take those 2 variables and we put them back into one of the 3 original equations, and then we'll solve for the final variable. And that's it. So let's actually do a problem here that has infinite solutions. So as we're looking at our system here, I've got 1, 2, 3 equations. I've labeled them. If we take equation 1 and we add it to 2 times equation 2, that will end up letting us get rid of the z's here. So let's do that. So equation 1 is x minus 3y plus 2z equals -7. And again, that's equation 1. Now we take 2 times equation 2. So 2 times 4 is 8x. 2 times y is just 2y. 2 times -z is -2z. You can see now that those are going to cancel when we add. And 2 times -5 is -10. So this is equation 2.1, we'll call it. It's not quite equation 2, but it's our newest version of equation 2. So now we add equation 1 and equation 2.1, and what do we get? Well, we get x and 8x are 9x. Negative 3y and 2y give us negative y. And we get plus 0 here. That's what we wanted. And negative 17. So now we have a new equation. And it is 9x minus y equals negative 17. We're going to call that equation number 4. So now we go back to the original 3 and we choose a different set of 2. So instead of choosing 1 and 2, let's choose 2 and 3. And we've got to get rid of the same variable z. So if we take equation 3, and we multiply equation 2 by 3 and add them, we'll get rid of the z's. So let's do that. So equation 3 then is 6x minus 5y plus 3z equals negative 19. And 3 times equation 2, 3 times 4x is 12x. 3 times y is 3y. 3 times negative z is negative 3z. And 3 times negative 5 is negative 15. And the top equation is equation 3, and the bottom equation is 2.2. It's not 2 or 2.1, it's 2.2. So now we add equation 3 and equation 2.2, and we get 6 and 12 gives us 18x. Negative 5 and 3 gives us negative 2y. We get a 0 with the z variable, which is what we wanted. And we get negative 34. So that gives us a new equation. 18x minus 2y equals negative 34. We'll call that new equation equation 5. Now we can use equation 4 and 5 and solve for x and y, because if you notice, equation 4 and 5 just have 2 variables. We have 2 variables, 2 unknowns, so we're back to the system of linear equations and 2 variables scenario, and we use addition or subtraction to solve for this. Let's take equation 5 and add it to negative 2 times equation 4. So equation number 5 is 18x minus 2y equals negative 34. That is equation 5. Now let's take negative 2 times equation 4, gives us negative 18. X positive 2y, because negative 2 times negative y gives us positive 2y. And that gives negative 2 times negative 17 is positive 34. And this is 4.1, equation 4.1. So now we add these 2 equations, and what do we get? Well, we get 0. We get 0 here for the y's. We have an equal sign, and what do we have on the other side of the equal sign? 34 minus 34 gives us 0. So we're left with no variables, and we have a mathematical statement here. Does 0 equal 0? Well, it does. Actually, 0 does equal 0. So that leaves us with a true statement. The variables dropped out, and we were left with a mathematically true statement. So that means we have infinite solutions. That's it. If you guys have questions, let me know. Thanks for watching.